Okay, so where we were up to last time was just getting started on Deutsch's algorithm. So basically what we've got here is, first example of a quantum algorithm that has a quantum speedup. And this is actually kind of not really a real life kind of example in the sense that it does something useful, but nevertheless, it's historically the first one. So this is why often this is the first algorithm that you'll encounter. Now, I discussed a little bit about what the actual problem actually is of Deutsch's algorithm. And so we were talking about basically a kind of a classification problem, right? So if you've got a binary function, so it's got two inputs. X is like a binary input, and fx is takes a binary output. Okay, so it's got two outputs. Now, in such a binary world, there's only four possible functions, and so I've graphed them here. There's these two blue ones, which we're calling constant because, well, it gives a constant, and the other two are so-called balanced functions because the number of zeros and ones in the output are equal. Okay? So basically, the aim of Deutsch's algorithm is to actually distinguish between these two functions. You're given one of these functions, you're promised that in, let's say, this black box here, and what we're going to try to do is to evaluate this box with as few calls of this box as possible. So classically, basically, you would have to evaluate this at least twice, because if you just only have one input here, then it could be any one of, say, this point, this point, this point, or this point. And in each of these cases, you just cannot distinguish whether it's in the balance category or the constant category. So that's the name of the game. And I still, said this many times, but, this is not a useful, like a task or anything like that. It's just sort of an abstract mathematical task. And that's basically what we're dealing with here. All right, so yeah, so I was talking about the classical solution to this problem. So in this case, basically you have to evaluate it definitely two times, because you need to evaluate for x equals 0 and to get the output of f equals f0, and then you need to evaluate for x equals 1, and then you'll get this value f1, and only then can you figure out which category it's in. So basically, the aim that we're trying to figure out is f of 0 equal to f of 1, or is f of 0 not equal to f of 1. So this is how we can distinguish between the two. But clearly from this equation here, the only way that you can actually distinguish it is if you know f of 0 and f of 1. I mean, otherwise you can't compare anything to anything. Yeah, so all right, so we definitely need two calls of the oracle in order to solve the problem. And basically the rough idea of how we're going to do this is using quantum superpositions. So this is how we're going to use this quantum oracle, where instead of just putting in like one value into the function at a single time, we're going to actually put in two at the same time. And so, obviously this means that this oracle here has to be, made of some kind of quantum material, right? So otherwise you won't be able to have this kind of superposition. But if this oracle is like such a sort of a quantum device, then in this case you're gonna be able to put in this kind of superposition state, and by the basically laws of quantum mechanics, if you put in this superposition, then what you're also going to get is this superposition out, right? So, you know, this is the big trick that you're going to be using in the quantum case, that you can put in this superposition. Obviously, classically, you know, there are no such superpositions, and so we don't have the opportunity to do this. So, you know, this looks like a neat trick, but there's several potential, you know, this isn't really the kind of the full solution, if you like, because there are several problems with this. So firstly, when you produce such a thing, you will only get like one of these outcomes at a time, right? So if you tried to measure this thing, you know, whatever f of 0, f of 1 is, you know, you just randomly get this, right? So you don't, when you do the measurement, you don't just automatically get both results. I mean, it's there before you make the measurement, but prior to, well, after making the measurement, you don't actually get both the results. So, you know, this isn't automatically a kind of a feasible quantum algorithm. Another problem is that when you know, producing such a box, actually some of these are like non-unitary operations. So for example, if you put in 0 plus 1, and let's say we've got this function f of x is equal to 1, right? So basically the output is 1. Okay, then we're going to end up with a bit of a problem here, because f of 0 is equal to 1, f of 1 is equal to 1, so both of them are actually equal to 1. And originally we had two states which are like orthogonal, right? Like 0 and 1 states are orthogonal, but 1 and 1 are the same states. So you sort of have this situation where, you know, 0 is, according to this box, 0 becomes 1, and 1 also becomes 1. So in fact, we can't really implement this box using a kind of a unitary operation. And well, quantum mechanics is determined by unitary operations. So this kind of means that we can't really implement this. So, you know, there's a couple of problems before we try to do the thing that we've got on the slide here. So we're going to fix each of these problems up one by one. Okay. So, so how can we make basically something which actually is a unitary, and you know, so it'll conform with the laws of quantum mechanics, and you know, we can still have this kind of superposition? Well, so we're going to do something a little bit similar to, if you remember some slides ago, we were, you know, we had a similar problem actually. So when we were talking about like the AND gates, you know, we had like the AND gate, we had like 2 inputs and 1 output, right? And this is definitely not unitary, because it's got like 2 inputs and like only 1 output, and it's just, you know, it's not compatible with something unitary. But we can make it potentially compatible by like kind of like copying one of the qubits over, or just not really copying, but just like, you know, letting this one kind of through, if you like. So it's basically unaffected from the beginning to the end. So we're going to do basically similar kind of trick to that, to try and make a unitary version of this oracle. Okay, so so let's consider this kind of box here. So we've got this like input box here, which is x, and this is going to be just sort of a you know, this is going to be the input of the original oracle here, right? So x is our input state, you know, just like the argument of the function here. Now we're going to have an extra qubit here, y, and this is the thing that's going to allow us to make like a unitary transformation. Okay, so if we've got this x input here, basically what this circuit here does is to basically find the action of f of x. So this is according to the 4 functions that we have. And then what we're going to do is, instead of just having f of x, we're going to add it into this this input here, y. Okay, so this y can be something else, but eventually we're going to actually just set it to 0. But let's just see basically what this whole circuit does. Okay, so this thing here is just like addition, but it's addition like modulo 2. Okay, so essentially addition modulo 2 is of course something like, you know, so 0 plus 0 is 0, 0 1 1 0 1 1, and if you add these modulo 2, then of course 1 plus 1 is 2, or in binary it's 1 0, but then, you know, it's like we just look at the lowest digit. So 1 modulo 1 addition modulo 2 is actually equal to 0. Okay. All right, so that's basically what that is. It's just this kind of binary addition of y. Okay, and we can see that actually this thing is this thing will be unitary, and in fact we can explicitly calculate the inverse, because you know, the unitary thing basically means that it has a kind of an inverse that is well, eventually just the transpose of the thing. So you know, unitarity means that the inverse is just equal to the transpose conjugate. So actually, in this case, this thing UF is completely, it's actually kind of a real matrix. And so that means that actually, in this case, it turns out that the U transpose is actually equal to U. And we can work out that this is, in fact, the inverse and the transpose of itself, because if we apply this twice, so imagine you've got like two inputs here, x and y. So these are all binary numbers. Like maybe I forgot to mention this. So this is all like 0 and 1. This is all 0 and 1. These are all basically qubits, right? And if you apply this unitary twice, then basically what's going to happen is, of course, so this top leg, nothing happens to it, right? So this x is going to be passed through all the way, because in this circuit, basically just x becomes x and nothing happens to it. So over here, of course, you know, it's x, right? And over here, it's going to be y plus f of x, right? And then if you pass through it twice, then when you do, when you pass it through twice, then basically what's going to happen is that this f of x is going to get added to this y twice. Right? So, sorry, just a sec. All right. And so when you add this y plus, so obviously there's two f of x is being added, but it's 2 times f of x. Now, when you're doing modulo 2, 2 times f of x is actually equal to 0, because, well, f of x can only be 0 or 1. So, you know, 2 times 0 is equal to 0, and then 2 times 1 is equal to 2, but modulo 2 is equal to 0. Okay, well, 2 is equal to 1 0, but we're only looking at like the lowest digit here, right? So 1 0. So actually 2 times anything is 0, and then y plus 0 is actually just y, right? So this is, so we've ended up at whatever the original states here are, x and y. And so basically this shows that this is its own inverse. So u squared in this case is equal to the identity. Okay. So this is how we can basically make a quantum version of this oracle, because this is now a unitary process, and actually right. So yeah. Well, okay. All right. So we can look at the examples here. Let me just erase this here. But yeah, I mean, if you look at the specific case of y being equal to 0, then basically what you're going to have is, of course, x, and then this bottom qubit is going to be f of x. And so if you just regard this as the output, then this is a more specialized version of the circuit, but it's still a reversible circuit. So, you know, we can implement it using quantum mechanics. So this is just explicitly looking at the 4 different instances of the circuit. So remember, there's only 4 different types of f of x here. So there's like these 2 constant versions and then 2 balanced versions. And so, so for example, for f of x equals 0, f of x equal to 0, then in this case, you have y, and you know, when we do this circuit here, what should be coming out here is actually, you know, f of x is equal to just this is actually equal to 0 here in this case, right? So in other words, in this circuit, the inputs are x and y as usual. The outputs are x and y. In other words, how we would actually implement this circuit is by actually just having 2 y's here. So basically what this is showing you is to, you know, how do you literally implement, you know, this oracle. Okay, so what about f of x equals to 1? So in this case, what you need to do is, so f of x in this case is equal to 1, right? And y, you know, given a random variable or just general variable y, y plus 1, you know, modulo 2, is actually just always equal to not y, meaning that, for example, if y is 0, then 0 plus 1 is 1, right? But if y is 1, then 1 plus 1 is 0. And so therefore, basically, y is basically the opposite, opposite of y. So this is like not y, right? Okay, and we know how to do like the opposite of something, the not. You just have to apply an x gate to it, and this will just, you know, flip the result of y into not y. X, nothing happens to it as usual, so therefore it's just a y. Okay. For this circuit here, or well, this function here, where we have f of 0 is 0 and then f of 1 is 1, we can implement this by a C naught gate. So we've already encountered this in maybe the maybe 2 slide sets ago. So what's going to happen here? So as you know, in the C naught gate, the control qubit, basically nothing happens to it. Right? So this x just passes through and becomes x. Meanwhile, y in a C naught gate, if f of x is actually equal to 1, then it will flip it, right? And so that's what happens in a C naught, but that's exactly what happens with this, because if f of x, so you know, f of x, this is equal to 0 if x equals 0, right? And so if f(x) equals 0, then y plus 0 is y, and basically, so if x equals 0, then you just get 1. Now, if f of x is equal to 1, which is what happens when x is equal to 1, then basically this will flip the y value. So it'll be not y. So this is again this thing, not y. So not y, so it's basically y if x equals 0 and not y if x is equal to 1. So this is exactly what the C naught does, if you remember. C naught basically flips this second qubit if x is 1 and does nothing if x is equal to 0. So this is exactly how to implement this particular circuit. Now, this one is basically the reverse of reverse function of the one that we just discussed, because f of x is actually 1 when x is 0, but it's 0 when it's 1, right? So we haven't done, or I haven't introduced this circuit yet, but this is like a alternative version of the C naught gate. Okay, so basically this is like the C naught gate, but if the control qubit flips it only if this value is 0, not 1. So this is like, I'm not really quite sure what to call it, but it's sort of like C naught, let's call it C naught dash, okay? And then, so the matrix is sort of, it looks like this, it's, oops, it flips it. So normal C naught looks like this, right? It's an identity for the upper block, and it's an X for the lower block, right? But C naught, alternative C naught, maybe I'll call it. Alternative C naught looks like this. It looks like a in this top 2 by 2, it looks like a knot, and then in the bottom 2 by 2, it looks like identity. So this is exactly basically what the situation is for this last function, where you know, it slopes down like this. So basically, in this case, because x is when x is 0, f of x is 1. So this is the case when basically f of x is equal to 1. And when you have like y plus 1, it basically flips it. So basically same logic as this stuff that I had here. So when x is 0, y will be flipped, and then you'll have like y bar. And then if x equals 1, then you're adding 0, and so this basically does nothing. So this alternative C naught is actually just how you implement. Does this make sense? Let me know if you.
Is this also the matrix of the C naught gate, like reverse? Like,
you're wondering about what the matrix is of this C naught, right? Like this one, yeah, right. Actually, no. So this one. So let's just quickly work out what the matrix of this one is. So we write the matrix elements like this in this order: 1, 0, and then 1, 1. Okay. So for this one, we look at the second qubit and then either flip it or don't flip it, depending on that, right? So here, what we're going to have, we look at the second qubit, and because this one is 0, we're not going to flip anything, and so that's why this element will be 0. This one, what's going to happen is that we're going to flip this one if this one is 1. Okay, so this 0, 1 should turn into 1, 1 actually. So this element will be 1. This one, the second element is 0, so this one will be like this. And this one, the second element is 1, so we're going to flip the first one. Okay, so sorry, that should be in the second column. So So it kind of looks sort of like this, if you like. Yeah. So somehow the the first and the third rows are diagonal, but then the second and the fourth ones are in this X-like configuration. So that's actually, yeah, yet another. Well, it's just different, I guess. Yeah, it's actually different to this phenol. Okay, but good question. Okay. Anyway, what this was basically trying to do was to just show you, like, exactly how you would implement these gates exactly. So when we call it like an oracle, it seems a bit mysterious, like, that not allowed to look inside like what the oracle is. It's sort of supposed to be this black box, but actually, there is a simple actual circuit that you can actually use to create it. And for this case, this is basically what the inside of the oracle looks like. That's why I've sort of shaded it kind of blue, so that it's sort of peering inside the actual oracle, right? So this is how you would actually do it. Actually, people don't even normally talk about this so much. How do you actually implement the oracle, because it's sort of supposed to be nothing interesting. But I mean, sometimes it's good to see exactly how things work on the on the insides. But I guess what it also shows you is that, well, I was going on about how this construction does make it a unitary circuit, but once you write it explicitly in terms of such quantum gates, you can see that it's definitely, yeah, well, it's definitely unitary. Okay, so hope that's reasonably clear. All right, so now that we've set up sort of the oracle, let's try and make use of it, and work out how we can use it to construct this Deutsch's algorithm circuit. Okay, so the simplest thing that you might try. So all this discussion was just to make sure we can actually make a unitary oracle. Okay, so so imagine now we've implemented this, and now again the task is to, so we've got 4 versions of the oracle. Somebody picks a random oracle out of the box. It's going to be like one of these 4. You don't know which one it is, and it's your task to try and work out which one of these 4, well, okay, which category each of these are in. Is it in this category where it's constant, or is it in this category if it's balanced? Okay, so that's basically the task that you've got. Okay, so okay, so let's try to do something like this. So the whole point of all this is that we can take advantage of quantum superpositions. So why don't we try and put in both of these input states of like X together, right, as a superposition? Because if we do that, then what you should get is a superposition of the output. So let's try making a circuit like this. Okay, so let's try and work through the circuit together and work out what you get. So as with any quantum circuit, what you can do always is to look at the state at any point in time. So here's my scroll bar. So I can work out basically what the state is any point. So at this point in time, state is just 0, 0. That's just the initial state. Okay, so that's the state then. Now, what about the state here? Well, after the first qubit has a Hadamard, and if you remember, Hadamard is a matrix that looks a bit like this. So it's 1, 1, 1 minus 1. So after the first Hadamard, basically what this does is that Hadamard acting on the state 0 will produce state plus. Okay, plus meaning it's a superposition of 0 plus 1. Okay. All right, 0 plus 1. Okay, so at this point, the state that we're going to have is equal to plus, and then the second qubit is the state 0. Okay, and now we're going to input this into this oracle. Now, let's now try and work out what's going to happen to this. Now, remember the way that this oracle actually works is that, well, maybe I'll just redraw it here. So the way that this oracle here works is that if you input some state like x, y, so remember these are the just like binary inputs, so it's like x and y. So here, x, this will output y, and then modulo f of x, okay? Where f of x is one of these 4 functions. You don't know which one it is, but you know, one of the 4. So let's look at the case when actually this input here is 0, okay? Because in this case, that's what we have. This is just 0. All right, so in this case, we've got 0 state, and this is 0 plus fx, and so this is actually equal to f of x. Okay, so if you just input 0 here, then the output of f of x is actually just output on the second gate here. So now what happens if you put in a superposition? Well, you will basically get a superposition of the 2 cases. So let's work out what you're going to have, you know, at this point in the output. So over here. So going into this, what we've got is basically 0 plus 1, 1 over square root of 2. And then the second qubit is 0. So this is what was input here, and we're going to apply this unitary u of f. Okay, and then so how we can always work this out is, you know, this thing is defined for each of the sort of you know, basis states, right? And so what we know here is that x 0 input, x and then 0 input with u will become x and f of x. Okay, so this is basically the action of the circuit. So because you know, once you have this superposition, you can just sort of expand this bracket here. So you'll have u of f applied on 0, 0, and then u of f applied to 1, 0. Okay, and then we can just use this relation that, you know, was the sort of the general case, and then just apply it to this each of these cases. Now what we're going to end up with is so u of f applied to x0, this will just become 0 times f of 0. And then this second term will be 1 and f1. Okay. All right. So this is just what I've already got as the answer here. So you can see how this works. Basically, you input a superposition, and your output will also be a superposition. It wasn't quite like the case that I wrote down here, previously. So I think previously, I was thinking like you input a superposition and then you just get output of the superposition. It doesn't quite look like that, but I mean, it's, nearly something similar, right? So you have basically each of these cases. Okay, so it's got an extra sort of index state, which is labeling what the cases are, 0 and 1. But well, we've still got these two outputs. Okay, so is everything clear before I just erase this? Okay, good. All right. So that's what we've got on the output. Now, so can we figure out whether it's constant or balanced using this state? Well, so the problem is that if we try to do a measurement on this state, and of course, that's the only way you can get information out of a quantum circuit, right? You got to perform a measurement, and if you want to perform a measurement, then, well, if you measure in the 0, 1 basis of, say, this first qubit, it's going to collapse to each of these with 50-50 probability, right? So, like before you do the measurement, you've kind of got the two outcomes there. It's right there in the state. Problem is you can't get it, like you can't measure it. You can't actually extract the results from there because whenever you do a measurement, you're only going to get one of these cases at the same time. And then actually we're back to square one, because the whole point of doing this was that we were trying to get both of these with only one application of this oracle. But because we can't actually extract both of them, we only extract one of them, probably half, maybe you're going to have to do this twice. And then, you do it once, perhaps you get this result, the f equals 0 result, and then you do it another time, and then you get the f equals 1, if you're lucky, that is. If you're unlucky, you keep on getting like f of 0 all the time, and it's actually worse than the classical case. So so this is basically the problem of doing it this way. So basically this approach doesn't really work. Okay. So let's sort of think outside the box here and see if we can do it a slightly different way. Okay, so imagine actually, so intuitively, putting the Hadamard on the first qubit seems to be what makes sense, right? But actually, let's just look at this other case of when we actually input superposition on the second qubit. And let's just look at the case when we start with this. So we start with a 1 instead of 0, and then we apply the Hadamard. Okay. We actually then end up with something a bit interesting, because when you apply this, and now, so this time X is not a superposition, it's just like either the 0 state or the 1 state. Okay, it's just a fixed state. Okay, and then when you perform this unitary, what's going to happen is, so X, the first qubit is X, right? And the second qubit, so remember the Hadamard gate looks like this. So we're looking at actually the second column of the Hadamard gate. So it's like this, 1, 1, 1, like this. So because it's the second column, it's the output of the state is going to be 0 minus 1, this state here. Okay, and then we apply this oracle here, right? Now, what's going to happen is that, well, as usual, if you input a superposition, then this oracle will execute all the terms in the superposition sort of in parallel, if you like. And so for the case where it's x, so there's two terms here. There's x0 and then there's x1. Yeah. So for the first term, because this thing is 0, then 0 plus f of x is basically what you're going to end up with for this term. And over here, it's going to be 1 plus f of x. Okay. Now, let's, f of x can only be either 0 or 1, right? There's only two cases here, basically. So imagine if f of x is 0, then what we're going to have is like 0 minus 1, because f of x, if this is 0, then you're just adding 0 to something. Adding 0 to, modulo 2 also does nothing. So 0 plus 0 is 0, 1 plus 0 is 1. So you're going to end up with this state, 0 minus 1. Now imagine if f of x is 1. So then it's going to be 0 plus 1. That's going to be 1. And 1 plus 1, that's going to be 0. Okay. And what we're actually going to end up with is these two cases. It actually looks almost exactly the same. So the final result at the end of this circuit here is x. This is minus state, right? And this is also minus state. Actually, this thing here is, minus state is defined as that. This thing is actually defined as minus of minus state. Okay. So actually, the only thing that's different here is that this has an extra minus sign. So the way that we can just write that is just by putting this factor of minus 1 to the power of f of x. Okay. And so we can summarize all that by saying that, okay, well, actually the action of this oracle, if the second qubit is minus, actually is like this. Uf of x actually gives an extra minus sign if f of x is equal to it gives an extra minus sign if f of x is equal to 1. Actually, maybe another way to view this is, so I did a very long-winded explanation, but maybe these days, another way that people might explain this whole oracle is just to say, let's just define an oracle with these properties. So say u of f is equal to minus 1 to the power of f of x. Okay. Now it's obvious that this is also a unitary operation. Remember, we were all worried that u might not be unitary or something like that. Now it's obvious this is unitary because, again, uf squared, if you just apply uf twice, then this is of course equal to 2 f of x, right? And then 2 of f of x is just 1, right? Squared minus 1 squared is 1. So it's obvious that this is unitary. So maybe, like, I think I explained it like this mainly because this is sort of historically how people sort of found this kind of thing. But in a way, you could save a lot of time and effort by just saying that, well, you can always define a unitary operation according to this function just by this definition. You can take the explanation that you prefer. So, all right. Anyway, if we go back to the sort of the original type of, I think this thing is called the phase kickback trick or something like this. Anyway, so when people discovered it, they sort of thought it was kind of interesting. So they named it after something, but actually it's very commonly used these days. So I think it's called phase kickback. So anyway, we can define so if we input minus 1 to the second input here, we can actually define the oracle, or the oracle has this action, and then, if you like, we can just forget about this second qubit, which is a minus, and then, just sort of more or less focus on the first qubit because, that's the only one that really is important. Okay. Now, using this this kind of trick, if you like, of putting in the minus sign on the minus state on the second qubit, we can actually now define well, the solution to this Deutsch's algorithm. Okay, so the basic idea is this. So if we now let's try to put in this superposition state on the first qubit. But you know what went wrong last time is that for the second qubit we just input 0. Okay. Now what we're going to do is we're going to put in this minus state on the second qubit, and let's see how it actually works this time. Okay. So so let's try this circuit now. And this is basically what will give us the final Deutsch's algorithm. So, so basically what's going to happen now is that, okay, so we're going to have this superposition input here, which is 0 plus 1. And this U of F gets applied to this state here. And there's also this state, but nothing ever happens to this state. So it doesn't really matter what this is anymore, to be honest. So this state is just always going to stay as the minus state. And basically nothing really changes. So I'm not even going to write it. I didn't really write it here, and we can just sort of forget about it from here. But what's interesting is basically what these phases here do. Okay, so when you input a superposition here, what's going to happen is that you're going to get, well, according to this sort of phase kickback thing, minus 1 to the power of 0 on this term, and then minus 1 to the power of f1 on this term. Okay, and if we break down what actually this will do, so let's just look at the 4 different cases of these four functions. Okay, so let's look at this first function, fx is equal to 0. All right, so we just have to look at basically what is happening to this first qubit here when it's output. So we're going to look at basically what is the state at this point here. Okay, so let's look at 4 cases. So yeah, there we go. All right, so because the resulting state looks like this, it's minus 1 to the power of f0, minus 1 to the power of f1. So the fx equals 0. So imagine we had chosen this oracle, fx equals 0. In this case, this is 0 and this is 0, right? So the resulting state on the first qubit is actually equal to 0 plus 1. Okay. Now, if f0 is 0 and f1 is 1, so this one will be always 1, but this one will be minus 1. Okay, so this one will be 0 minus 1. If f of x is 1, then this one will be minus 1, and this one will be also minus 1, or it'll be this state. And finally, if it's this last type of function, then f of 0 will be 1. So in other words, this phase will be minus 1. And f of 1 will be 0. So this one will be plus 1. So the state will be like this. Okay. Now, what you'll notice is that this state, the cases where it's balanced, either case, it will give the state which is up to a global phase, basically equivalent to this minus state here. Okay, this one is also equivalent, well, it's minus of minus state, but global phase doesn't really matter in terms of measurements. This one will be like minus of the plus state, and this one will be just equal to the plus state. Okay, and so this is why there's this final Hadamard here, basically just to convert this plus state or minus state into 0, 1 basis. So we've got plus state, minus state. This will produce either 0 state, 1 state, minus 0 state, minus 1 state. And because these global phases don't matter, when you perform this measurement, basically, if it's this case, with 100% probability, you will get this outcome, right? So when you do this measurement here, because it's literally 0, you measure 0, so of course you get 0, right? So with 100% probability, you get 0. Here, with 100% probability, you will get 1, right? Here, with 100% probability, you will get 0. And with 100% probability, you'll get 1. Okay. So basically, in all cases, it doesn't matter which oracle is chosen, you will, with 100% probability, get this signal that, you'll, if it's this one, you'll definitely get it as 0, right? So if this one, you'll definitely get it as 1. And this is exactly in the right, correlation, or, where you get 0 are exactly where you get these constant circuits, and where you get 1 is exactly where you get these balanced circuits. So actually, we can distinguish these two cases with only one call of the oracle. So basically, all this discussion while we've been talking about this is, in this circuit, there's only one call of this box here, right? We only used it once. I mean, yes, we put in a superposition into it, but I mean, in terms of like how many times you had to use it, well, it's only once, right? And you managed to actually get the, you can distinguish between the constant and balanced cases with only one call of this. And so, voila, that's Deutsch's algorithm. Any questions at this point?
Yeah, like what's the use of the second what's the use of the second H gate?
Yeah, second. Yeah, so the use of the second H gate is just it's for this particular definition of the oracle, right? So remember, how do we get at this oracle? Well, we were complaining that, well, if I tried to make a oracle like this, this is not unitary, okay? So I can't make this oracle because it's not unitary. Okay, I can get around that by making like this, adding the second qubit to it. It's a bit like that whole trick with, the AND, classical and digital AND gate. It's not reversible, but I can kind of like copy one of the inputs and then make it a unitary gate. So this is a similar trick where I can make a reversible version of the oracle. This one didn't work, but this one is a reversible version of the oracle, but it takes like 2 inputs, okay, in order to make it reversible for all cases. If it's like a 1 qubit, this is like trying to make it like a 1 input, 1 qubit input, 1 qubit output, and basically it's just not, you can't make it a reversible gate. But with a 2 qubit, where you kind of like copy one of them, yes, you can make it a unitary gate. And so this is why we basically use this one. Now, the second qubit, we tried basically putting this in 0 state, but actually that didn't really work. But there's this trick where if you input the minus state to it, actually nothing kind of happens to the second qubit. Like it's minus at the beginning, it's minus at the end, but it allows us to use this like two qubit oracle. And so it's a kind of a little bit of a long explanation, but that's basically why we have this second qubit. I mean, originally it was because we were trying to make like a reversible version of this gate. Now, maybe another explanation. So the way I explained it was kind of a little bit like historical, because that's actually how it was originally discovered. Like maybe you might like a different explanation where I just say, okay, well, even though this this one is not a unitary kind of operation. Okay, well, instead of that, why don't I define a why don't I define it differently? Why don't I define it like this? So you have x, and then instead of it being a, you know, like instead of it the state, it's like state itself being changed, right? Here what we were trying to do is to say, okay, if the input is x equals 0, then the output is f of 0, okay? And then this is why we ran into problems with unitarity, right? But if we actually define a unitary like this is actually a perfectly good unitary gate, okay? And so why don't, maybe another explanation is just to define a unitary according to that, and just say, well, hey, this is a unitary operation, so therefore that's going to be my oracle. Okay, so that's a little bit more of a straightforward explanation, and doesn't it's a bit quicker, but actually historically this is how it was discovered, so that's why I explained it in this way. So yeah, the short form of the answer is basically nothing really happens to that second qubit, and you don't really need it actually. If you defined it like this, you could just ignore the second qubit to start with. It's kind of historical in its origin.
And also, like for the final algorithm, like we have this three Hadamard gate, three Hadamard
Oh yeah.
things. So it's like before we know that after putting the Hadamard on the second qubit, the change actually. So so like why we put it 3 times on.
What's the purpose of the last one? Yeah, so like if you work out what happens at this point in the circuit, so if you just look at here, what the state is at that point is basically summarized by this element of the table. Okay, so if it's like the first function here, then the state will be 0 plus 1. For this one, it'll be 0 minus 1, so forth. Okay, now in the previous slide, I think I said that there's a sort of a standard form of the kind of circuits. Okay, so I've slightly broken the standard form, but I've the standard form that I was saying was basically initially all the qubits are 0, and then I input here's my U algorithm, and then at the end I'm going to perform a measurement on all these qubits, and in the 0, 1 basis. Okay, so I guess, okay, I didn't quite follow standard form, but nearly standard form. The only difference here is that this input state was 1, not 0, but I could easily fix that if I wanted to. But here, I guess I'm sort of trying to stick to this standard form where the measurement is always made in the 0, 1 basis. Okay, and then remember there was that whole discussion of if I wanted to measure in a different basis, then what I can do is to combine this like rotation with, so this is the measurements. I can combine the rotation with the measurement, and then basically I can measure in a different basis. Okay, so this is exactly what's happening. So this combination of performing a measurement and then Hadamard before is basically what that achieves is I'm measuring in the plus or minus basis, okay? And because finally what we've got here, what we want to do is measure in the plus or minus basis, because this this thing is equal to plus, you know, this thing is equal to minus, this is equal to minus plus, and so forth, right? So we can see that actually what we've got here is actually exactly the, you know, sort of the you know, the answer that we want is right there actually, so long that we measure in the plus or minus basis. And so what we're doing is kind of to well, you know, you can view it as like this is measuring in the plus or minus basis. Another way to view it is that you're going to like do a further rotation. So applying this Hadamard rotates it from plus to 0, and then rotating this goes from minus to 1, right? And so by finally putting it in the 0, 1 as the output, then when you do this measurement, you know, you just measure the 0 and the 1, and that's it. So basically the purpose of this last one is just to measure in the right basis. The purpose of this one is to kind of make that superposition. So you evaluate the oracle twice. And then the purpose of this one is kind of somewhat historical, because you know, this is how people define the oracle originally, but actually you just about don't need it, because you could define the oracle in a different way, and then that would be the end of the story. Yeah.
Right. Yeah.
Okay, hopefully that's clear.
Yep.
Okay, all right. Well, we can keep on talking. Have further questions, but yeah, all right. So I think, yeah, for today, this is the last slide of this set, but I'm not really going to properly introduce it, but you know, just it's a kind of a generalization of what we were talking about. So so the this Deutsch's algorithm is kind of, okay, it's, as I said, it's not really a very, not like a useful circuit, but it does show some kind of quantum speed up, because you only have to evaluate the oracle once. Basically, if you say, okay, what is the quantum speed up of this thing, then it's like a 2 times speed up, because, you know, classically we have to evaluate this thing twice to figure out, you know, it's constant or balanced. But in the quantum circuit, you only have to evaluate it once, right? Okay, so it's 2 times versus 1 time. So basically it's twice as fast. Okay. Well, that's okay. It's not like super impressive. Like, okay, 2 times faster is good, but it's not like super fast, you know. And so what people thought of is, okay, well, can we like try to make a version of this so it's not just 2 times faster, but, you know, maybe it's like exponentially faster. Like, you know, if there's like lots more qubits involved, perhaps we can even make it, you know, 4 times faster, 8, 16, 32, you know, as many qubits as you have. And so this is basically the generalization to lots more qubits. So basically the previous case was, well, okay, had 2 qubits, but one of them didn't do anything. So it's sort of like a 1 qubit example, actually. Now, this is generalizing it to m qubits. And basically what this does is to make the speed up actually 2 to the power of m faster. So actually, you know, it will be, you know, exponentially faster than a sorry. Okay, so how it works is a lot like basically the same circuit, but just sort of, you know, generalized. So imagine you have an oracle that looks something like this. Oh, sorry. I should define what the problem is first. So problem looks something like this. So again, we've got this binary output function. Now the input is not just binary, but input has sort of m bits to it. Okay, so if it's got m bits, there are 2 to the power of m different input results. So maybe you can think of this sort of as f of sort of x1, x2. It's like a multi-valued, multi-bit input. Okay, and because each one of these binary variables, x1, x2, they can be 0, 1, and so there's like 2 to the power of m combinations on the input here. Okay, the output is still either 0 or 1. Okay, so we're going to have these functions, and there's actually going to be all kinds of different functions. The constant ones are the ones like before. We have it's all 1 or all 0, and the balanced ones have an equal number of zeros and ones, but you can see this time there's going to be a lot more combinations of these balanced ones. So actually there's going to be, well, how many? Well, there's probably something like binomial m over 2 numbers of balanced functions. So there's a lot of balanced functions. There's only two constant functions, but still the task is to figure out, so is this function balanced or is it constant? Okay, and basically classically is the only way to really be 100% sure. So I mean, you can make a guess, and the fact that there's many more balanced functions and constant functions, it depends on how you sort of do this randomly, but classically the only way to be 100% sure that you've got, say, a balanced function or a constant function is to at least evaluate, well, probably like half of these ones, right? Because if this is guaranteed to be balanced, and then say you just pick them at random, right? Like these inputs. Now you could be incredibly unlucky and just like pick all these cases where it's like say equal to 1. Okay, so say it's this blue one here, and then say unfortunately you picked 1, 2, and then this one and this one and this one, right? So the only way you could be 100% sure that it's balanced or constant is by actually doing this, at least, I guess, 2 to the m divided by 2, maybe plus 1, okay, different cases, right? And if you did it for that many cases and it was, say, constant, all giving the same values, then you could be sure that it's definitely constant. But otherwise, you can't be sure that it's going to be balanced or constant because you need to evaluate all these. All right. Again, it's a bit of an artificial problem, but well, it's the nature of it. Right? So, so classically, you need something like an exponential number of these ones in order to work out how many, whether it's constant or balanced. Now, in the quantum case, you do something very similar to what we've just discussed. We set up an oracle like this. Again, have the input like this, so the input is just the minus state. And then we input this superposition state here, and we evaluate this. And then eventually what we're going to do is put this Hadamard gates, perform this measurement in this plus or minus 1 basis. And then we can figure out whether it's constant or balanced. And this is sort of like a 2-qubit example here. So imagine if, so we've got like, say, 2 qubits here. And what this U of F does is basically pull out this phase -1 to the power of F00 and so forth. And basically, if this thing is constant, then basically all these phases will be the same. Okay. And if all these phases are the same, then right, yeah, then basically this one will have like the, it'll be, so if it's constant, like this term here will be the same as like plus plus, okay? Because when you do plus plus, this is like 0 plus 1, 0 plus 1 times 0 plus 1. And you'll get basically all these 4 cases with all the plus sign. And so basically the phase of all these are the same. Okay. Now, if it's balanced, then you're going to have some of these with a minus sign, because some of these ones will not have the same value as the other ones, right? So some of these will be minus. And so you're going to have some cases of this, like it'll look something like, plus, minus, or something. And the fact that you got a minus here means that, it's a balanced function. It's the only way that it could be balanced, because, that's how you get like an opposite phase over here. So the signal of a minus state over here will indicate that it's balanced, and essentially you've still only evaluated this once, okay? So this oracle only needs to be applied once, and you sort of did this kind of parallel evaluation of the state, which classically you couldn't do. So basically you can still, you can get a quantum advantage in this case. Okay, so I think that's it. Any questions?
Do we have 14 or 15 homeworks? I saw that the 15th homework is basically like blank.
Oh, are we up to 15 already? I talking about the total.
Yeah, I'm just talking about the total one.
Total, right? Okay.
Just curious that the 15th one is almost blank.
Oh, yeah, I think it's 14 then. Okay, so yeah, I think I can only remember there being 14. Let me have a quick look.